Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're going to go through this particularly scary-looking integral. About a week ago, I was working with a student, and he was going through just generic techniques of integration, that kind of stuff that comes up in Calc 2. And as I was looking through some sample problems in my textbook to give him, this one jumped out at me. I think my initial reaction when I just saw this there in the textbook was, oh God. And my student knew that whatever was going to come up next was something of a doozy. And here we have it. You can see it on the screen. Integral of square root of 1 plus square root 1 plus square root of x dx. So how do we go about this? Well, our first u-substitution, and you know it's going to be bad when I talk about the first of the u-substitutions we're going to be using. First u-substitution is 1 plus square root x. Obviously, you'll want your u to be something useful, but also not too terrifying looking. So it turns out square root of x on its own doesn't help all that much, but 1 plus square root of x does. So u equals 1 plus square root x. du equals 1 over 2 square root x dx. Isolating for the dx so that we can plug it back into our integral, we get 2 square root x du. And the next thing we'll point out is that to get this entirely in terms of u, if u equals 1 plus square root of x, then square root of x equals u minus 1. So this 2 square root of x becomes 2 times u minus 1. So dx equals 2 u minus 1 du. Next, we have integral of, so now we have integral of square root of 1 plus square root u times 2 times u minus 1 du. And you'll notice, all right, we've simplified down our square root expression. Let's try it again. So now I'll say v equals 1 plus square root of u. And just like before, dv equals 1 over 2 square root u du. du equals 2 square root u dv. du equals 2v minus 1 dv. Again, we're doing just the same analogous substitution. If v equals 1 plus square root u, then square root u equals v minus 1. We have a square root u here. We just use it as v minus 1. The next thing we have to worry about is this u over here that shows up in the u minus 1. We point out that if v equals 1 plus square root u, square root u equals v minus 1. So u itself, that's just the square root of u squared. U itself is v minus 1 squared, which is v squared minus 2v plus 1. So we have v squared minus 2v plus 1 for our u. Our plus 1 and our minus 1 cancel. We just get a v squared minus 2v. So we get square root of v times 2 times v squared minus 2v times 2 times v minus 1 dv. All right. Now it's just a matter of cleaning up the mess. We can distribute our square root of v, or v to the 1.5, across all here. We FOIL this out. We end up getting 4 times v to the 3.5 minus 3v to the 2.5 plus 2v to the 1.5 dv. And that gets us 4v, we anti-differentiate, we get 4v to the 4.5 over 4.5 minus 12v to the 3.5 over 3.5, because this 4 times this 3 get us a 12. Plus 8v to the 2.5 over 2.5, because this 4 and this 2 multiply together to get us an 8. And then, of course, we have the arbitrary plus c, because we always have that with indefinite integrals. And finally, we combine the substitutions, right? We said that v was 1 plus square root u, we said u was 1 plus square root x, so that means v is 1 plus square root 1 plus square root of x. Now, in theory, we could have just done this substitution way back at the beginning, but it would have been unclear whether or not that substitution was going to clean up nicely. Whereas by doing it in those bite-sized pieces, it becomes a little more. We get a better indication that the move we made actually is making this simpler. And now we just have to shove that back in. So we get 4 times 1 plus square root 1 plus square root of x to the 4.5 over 4.5 minus 12 times 1 plus square root 1 plus square root x to the 3.5 over 3.5 plus 8 times 1 plus square root 1 plus square root x to the 2.5 over 2.5 plus c. You might be able to simplify this down further, but in most formats, at least within the United States, leaving something in this form would be good enough. And so that's how to handle that scary looking integral. And as always, if you like the way I explain things and wanted to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.